Hello class, this is Mr. Goodman, and this is lesson 4.2, the application of trigonometric ratios. So we've learned how to use SOH in somewhat of an abstract format, and truthfully, you don't just get perfect triangle or right angle triangles and then ask to find the missing piece of information. You have to create the triangles, you have to draw the triangles based on the situation that's being presented. So today we're going to go over a couple situations. There's not too much new here, it's just application. And that's what we're going to do. So let's get to it. The very first thing is that, the new thing at least, or something that you're being reminded of, is that there's an angle of elevation and an angle of depression. This is a picture of an eye, and when you're looking straight out, it's called the horizon. And when you look up, that's the angle of elevation. It's how much you're looking up. And if you're very close to the CN Tower, your angle of elevation is very large because you're looking up. Versus if you're very far away from it, you just have to look up a little bit. So your angle of elevation is just a little bit. When it comes to angles of depression, these can be a little bit tricky, and probably the only hard thing in this lesson. And as I say, it'll seem easy, but in this question down here, number 2, you'll see why it's challenging. Of course, if you're looking straight out, it's the horizon. And then if you look down, that's your angle of depression. Okay, so let's get to it. I'm going to pick and choose which questions I actually go through, but I'll definitely start here with this first one. So we have a point that's 25.4 meters away from a cliff, and a clinometer is used and find that the top of the cliff is at an angle of elevation of 72.5 degrees. So what's the height of the cliff? Now, because of a lot of these I'm drawing these out, you're probably looking right here and you're like, that's an easy question. I get it. I see the triangle. But what if this wasn't here? What if you had to create the triangle? That's really the only challenging part of these questions. So try not to fool yourself into thinking this is easy. I'm giving this to you right now, but you really should try doing this without seeing the answers first. In this case, we obviously label what we have. We're missing that. We're looking from this angle. Therefore, our opposite is unknown. Our adjacent is known. That's why we use tan. And we solve it and figure out the cliff is 80.6 meters. Easy stuff. Angle of elevation. What about angles of depression? So there's an airplane flying at an altitude of 5,000 meters. There's the airplane, 5,000 meters high. The angle of depression from the airplane to the airport is 3.4 degrees. So here's the fatal mistake that people often make. They'll create the triangle. Here's the airport. And sorry, the question's asking how far is the airplane horizontally from the airport. So that's this distance right here. And they'll say, I know, it's 3.4 degrees right here. But no, the angle of depression is starting from a horizontal. And how much did you have to dip down? So that's the only really challenging part, I think, of this lesson, is to know that this is 3.4, not this. Once you understand that, you can go about this question a variety of different ways. You should also know that because of the alternate angle theorem, these are parallel lines, therefore this is also 3.4 degrees, if that helps you. In any case, we know this angle, we know this adjacent side length, and we're looking for this opposite side length. So, tan, that's what we're going to use. And we use tan, and we figure out that the airport is 84,000 meters away, or 84 kilometers, because I think that's what it asks for, the nearest kilometer. Okay, move on. What else do we have? Construction of a roof. There's a roof. The pitch, how steep it is in 712. That means a height of 7, a length of 12, halfway from the midpoint. And it's asking what's the angle of inclination. So again, once we draw this out, you can see we've got an opposite and adjacent. Again, we're using tan. Go figure. And we figure out that the angle is 30 degrees, 30.3. When it comes to getting the answers in terms of degrees, it says here to the nearest degree, but I just personally like to put to the nearest tenth of a degree. You don't have to, because this question isn't asking for it, but I just like being in that habit. Here's a question about a ladder being up against a wall. It's the angle of the ladder makes with the ground should be between 70 and 80 degrees. So we don't actually know what it is. We know the ladder is 10 meters long, and we know that it's 1.5 meters away from the wall. So what's the angle of elevation to the wall? So again, in this case, I'm no longer labeling my sides. You should know this is adjacent, this is hypotenuse, therefore you use cosine. This is a missing angle, so once we get to this point, we're using our second function button. Just quick reminder, second function and then cos, which gives us our little -1 there. And that gives us our degrees. We could reverse this and say the ladder is at an angle of 75 degrees to the ground. The ladder is 6 meters long here. How far away is it from the wall? And again, it happens to be cosine, and then we cross multiply, and that's what we get for how far it is from the wall. At this point, if I were actually facing a class, I'd say, am I going too fast here? I know this is review, but maybe I'm going too fast. But I can't get that feedback, which is frustrating, I will say. At the same time, you can rewatch this, so if I am going too fast, just go back to it and watch it again. Somewhat harder questions here. And they're only harder because, again, these triangles aren't usually drawn for you. But in this case, we have two buildings that are 20 meters apart. 20 meters. Now, from the top of the shorter tower, the angle of elevation to the taller tower is 20 degrees. There it is right there. And the angle of depression from here is 45 degrees to the base of the taller tower. Again, this is 45 degrees, not this. And the question is asking, what's the height of this tower? Well, the height of this tower is this length plus this length. And I even took this question and drew it out for you as two separate triangles. Because if that's 20, that length has to be 20. Therefore, this is 20 and that's 20. So now that I draw it out for you like this, it should be pretty obvious how you're going to solve for x and how you're going to solve for y. But without it drawn out like this, perhaps this would have still been a little bit challenging. Once you see how you just took that 20 and brought it up here, and that the fact that you just need to find these two lengths, once you see that, it should be pretty easy. And you understand why this total height is 27.3. This is the last question, and it is a little bit harder, again, only because of the way it's sort of structured. What I'll say is, well, you're at the top of a cliff, 200-meter cliff, so it's 200 meters high, and there's two boats in the water. Boat number 1 is at an angle of depression of 20 degrees, right there, and boat number 2 is at an angle of depression of 25 degrees. So 20 degrees for boat number 1, 25 degrees. And I know that boat number 1 is further away because the angle of depression is smaller. So that's how I kind of know that. I also know that if this is 20 degrees, because of the alternate angle theorem, those are parallel lines, this 20 degrees this also has to be 20 degrees. And that's probably a key insight there. If you didn't have that, what you would probably end up doing is saying, well, if this is 25, then this has to be 65 right here. And if this is 65 and that's 90, that's 25. And if that's 25, that's 55. And if that's 155. Like, you figure it out, but it's much easier just to use the alternate angle theorem to just kind of go Z pattern, and there it is. Same thing with this 25 degrees, Z pattern, and 25 degrees right there. That's ultimately probably what would hold some of you back on actually going forward with this question. And sorry, I've talked so much, I didn't even say, what are you looking for here? What you're looking for in this question is the distance between boat number 1 and boat number 2. Basically, x is the distance here. Sort of, this is this question, and then this part is the other part. What I did is I took the two triangles. Think of one triangle here where the corner is 20 degrees, I redrew it here, and another triangle where the corner is 25 degrees, and I redrew it here. The first triangle encompasses this triangle, but we don't draw it. This is triangle number 1, right there. This is triangle number 2, right there. Now, if this entire length and this entire length are subtracted from each other, then what's left over will be this little bit here. If this is 30 meters long and this is 20 meters long, this leftover bit is 10. So essentially, A minus B is going to equal our answer. So let's find the length of A and B. Again, this is tan, opposite and adjacent. So we find out the length of A is 549.5, and the length of this tan, opposite and adjacent, is 428.9. When we subtract those two from each other, we get an answer of 120.6 meters. I should really write that. So that's how far the boats are from each other. Again, this question, once I set it up with the triangles, was really easy. But the key was understanding those angles of depression and alternate angle theorem, and that if this is 20, that's 20, and if that's 25, that's 25. So there are a couple insights here on that question that could have made it a little bit more difficult for you to solve. Okay, I'm going to wrap up because, as always, I think my videos are limited to 12 minutes for some reason, but you know what? That's a good thing, because you don't want these going for too long. Homework, TOA type questions. I'll tell you which ones you need to do. And special bonus feature. Have you ever wondered what $5 bills used to look like? Well, wonder no more. Here's a bunch of $5 bills and what they used to look like. This one is the one that came before that, so this is 2006, this is 1986, this is 1973. And there's the current one there. Used to have people playing hockey on the back. This is when I was in university, and when I was in high school, it used to be a kingfisher bird on the back. And before I was born, it was some people fishing in a boat. So yeah, now you know what $5 bills in Canada used to look like. I hope you enjoyed that special feature. I hope you enjoyed your Victoria Day, and that you noticed that I didn't post any homework due for Monday because of that. That's the last time that'll happen, and then we're going to go strong Monday, Wednesday, Friday from now until the end of the school year. So that's about it. I hope you enjoy your Victoria Day tomorrow, or whenever you're doing it, and that you have a good week. Okay, Mr. Greenman, signing off.